Okay, good morning. Welcome to
KidMath number 108.
KidMath number 108. So we're in the middle of a fun sequence trying to find a formula for the Fibonacci numbers. And remember, we're saying the Fibonacci numbers are defined by this formula, fn plus 1 equals fn plus fn minus 1. F of 0 is 0, f of 1 is 1. Okay? Those are the Fibonacci numbers, and we can go 0, 1, 1, 2, 3, 5, right from there.
Yep.
And then we also did this idea. We said this looks like an exponential, and we said, well, what if this was lambda to the n? That Fibonacci number n looked like lambda to the n. And we found yesterday in KidMath107, we found lambda would have to satisfy this equation, lambda squared minus lambda minus 1 equals 0. Which meant that lambda, using the quadratic formula, was 1 plus or minus the square root of 5 over 2. So there's two possible lambdas that satisfy this. I went a little bit too fast. It was a constant times lambda to the n, right? Because we could always multiply by a constant and make it still work. So that's where we left off yesterday. So what we're going to do now is say, well, we found two solutions, so let's see what that might be, okay? Okay, so I'm going to say that the Fibonacci n is some constant 1 times 1 plus the square root of 5 over 2 to the n, plus constant 2 times 1 minus square root of 5 over 2 to the n. Now this looks very complicated.
Yeah.
Two pretty complicated numbers, two different constants, and our Fibonacci numbers. So before we dive into this, let's just say what this says. The nth Fibonacci number is a constant times this number to the nth power, plus a different constant, or maybe it's the same, who knows,
Yeah.
times this number to the nth power. Now, what are the two easiest Fibonacci numbers we should check? What two n's would be really easy for us to check?
These two, 0 and 1.
0 and 1, right? So what's anything to the 0 power?
Anything to the 0 power is automatically 1.
So the Fibonacci 0 equaling 0 says this constant, C1 times 1, plus C2 times 1, is 0. Well, that's nice. So the two constants have to add up to 0. Fibonacci 1 equaling 1, what does that say?
That says C of 1 times 1 plus the square root of 5 over 2.
Okay.
Plus C of 2 times 1 minus the square root of 5 over 2. So
What does that equal?
we can.
What does this equal?
Well, these just cancel.
Well, hold on a second. This is something.
Yeah, this should equal 1.
This should equal 1 because that's Fibonacci 1. Fibonacci 1 equaling 1 says this should equal 1. So I have these two equations. Okay? They add up to 0, and then this complicated sum equals 1.
Yeah, well.
Okay? I guess I'm going to have to go up here now. So sorry, we don't have a whole lot of board space. This equation's easy, right? C1 plus C2 equals 0. What do you think? What's something you'd like to do to simplify this equation?
Well, if we could factor out, like, something, we could square everything, maybe.
Ooh.
To get rid of the square root.
That's going to be super hard, actually, because you're going to have to square everything on this side, which means you would have to put brackets around it like this and square it. Too much. You could get rid of something on this. What's the first,
Maybe get rid of the denominators.
Yeah, so what should we do?
Multiply everything by 2.
Multiply everything by 2, so we're going to have an equation that equals 2. And now we have a 1 plus the square root of 5 and a 1 minus the square root of 5.
But those just...
Well, they have different constants. So let's group the things without the square root of 5 and with the square root of 5. So we're going to have something equaling 2, because we just multiply everything by 2. Okay, look at the integers. C1 plus C2. Those come from the integers, this part and this part. And what about the non-integer part?
Plus the square root of 5 and minus the square root of 5.
And what are those multiplied by?
Those are multiplied by C1 times the square root of 5 and C2 times minus the square root of 5.
Okay, so I'm going to say square root of 5 times C1 minus C2.
Alright.
Okay? So this complicated thing down here actually simplifies pretty easily, and it simplifies even more because what do you know about C1 plus C2?
That's just 0.
That's just 0. So this whole thing actually just goes away because of the first equation. Now what can I do to make this equation a little easier?
Well, you could divide everything by the square root of 5.
Yeah. So now I'm going to have C1 plus C2 equals 0, and C1 minus C2 equals 2 over the square root of 5.
Maybe we should rationalize this.
Let's just leave it.
Okay.
Too complicated. Now I have a pretty simple system of equations. What do I do to solve this?
You can add them.
Okay, what do I get?
You get 2C1 equals 2 over the square root of 5.
So what does C1 equal?
C1 equals 2 times the square root of 5 over 2.
Which is sometimes known as
1 over the square root of 5.
1 over the square root of 5. And if C1 equals 1 over the square root of 5, how can we find C2 really quick?
C2 is the same thing. Oh no, C2, you can just plug it back into this equation.
Or
this top equation.
which is easier?
This top equation.
Why?
Because you have a plus instead of a minus.
Okay, so what does C2 equal?
C2 is minus 1 over the square root of 5.
Okay, so we found our constants. They turned out to be really simple, right?
Yeah.
So we just found a formula. We just found it. We just found the formula for the Fibonacci number. The Fibonacci number n equals 1 over the square root of 5 times 1 plus the square root of 5 over 2 to the nth power minus 1 over the square root of 5 times 1 minus the square root of 5 over 2 to the nth power.
Yep.
That's amazing, right?
Yeah.
Right? That's amazing. We just found a formula for the Fibonacci numbers. You believe it?
Yeah.
So now, before, if we wanted to find Fibonacci number 100,
You have to add it all up.
previously we have to find all the previous Fibonacci numbers, 99, 98, 97, 96. Now we can just take this number to the 100th power. Wait a minute.
That might be a little hard.
Maybe that's not a lot easier. But who could do that really easily for us?
A calculator. Or a Wolfram Alpha.
Wolfram Alpha. So we'll play around on Wolfram Alpha tomorrow with this because we probably got up to 5 minutes anyway. But here it is. Here's our formula for the Fibonacci number. And do you recognize this number, by the way? 1 plus the square root of 5 over 2?
I think that's the golden ratio.
It's the golden ratio. I asked you yesterday and you didn't recognize it, but it is the golden ratio. So the Fibonacci numbers are somehow related to the golden ratio.
Which means they're related to rectangles somehow.
Somehow. Maybe there's some way we can make a cool rectangle out of Fibonacci numbers.
Yeah.
You think we can do that?
Maybe, but I always thought they were spirals.
Yeah, well, we'll see. Okay. Well, so tomorrow we'll go off to Wolfram Alpha and play around with this formula. Okay?
Alright.
All right. Good job, hun. Good job.